Welcome to Section 6, Lesson 7. In the previous 6 lessons, we built every tool for solving linear systems: graphical, substitution, elimination, method choice, special cases, and 3 variable extension. Today, we apply the system solving toolkit to word problems where 2 or more unknowns interact through 2 or more constraints. Word problems with systems are the main practical use of the system, solving algebra across science, engineering, finance, and business, and recognizing the system structure inside an English description is the central craft skill of applied algebra. Today we lock in the 4-step framework adapted for systems and walk through 2 examples illustrating common system word problem templates. First idea on the board. A word problem requires a system of equations when there are 2 or more unknown quantities related by 2 or more constraint statements in the problem. Each unknown gets a variable name, and each constraint becomes one equation. With 2 unknowns and 2 constraints, you build a 2-variable system that the Section 6 methods can solve directly. The translation step is the same words to algebra workflow from Section 2, applied separately to each constraint and producing one equation per constraint. Second idea. The 4-step framework from Section 3, Lesson 9 adapts cleanly to systems. Step 1. Define a variable for each unknown quantity in the problem with explicit units. Step 2. Translate each constraint into an algebraic equation, producing as many equations as there are constraints. Step 3. Solve the resulting system using the appropriate method from Section 6. Step 4. Back substitute and verify the values in the original English context. The framework handles any standard word problem with multiple unknowns. Third idea. Several common templates account for the majority of system word problems in algebra. The number value template applies when one constraint counts items and another sums their values, like coins or tickets of different denominations. The mixture template applies when 2 solutions of different concentrations combine to produce a target concentration. The distance, rate, time template applies when 2 moving objects relate through their distances, rates, and times. The age template relates ages of 2 or more people through past or future age relationships. Recognizing the template instantly tells you the structure of both equations without having to derive them from scratch. Word problems with systems require a system of 2 or more equations because 2 or more unknowns interact through 2 or more constraints. Each unknown gets a variable, each constraint becomes an equation, and the system-solving methods from earlier in this section produce the values. Here is the 4-step framework adapted for systems. Step 1. Define one variable for each unknown quantity, with explicit units written next to the variable. Step 2. Translate each constraint statement into one algebraic equation. Step 3. Solve the system using substitution, elimination, or graphical method as appropriate. Step 4. Verify the solved values in the original English context. The number value template applies to problems involving items of different denominations. Constraint 1 counts the total number of items, x plus y equals total count. Constraint 2 sums the total value ax plus by equals total value, where a and b are the per item values of each type. The 2 equations together form a clean 2-variable system. The mixture template applies when 2 solutions of different concentrations combine. Constraint 1 gives the total volume Ex plus y equals total volume. Constraint 2 gives the total amount of solute x plus by equals c times the quantity x plus y, where A and B are the source concentrations and C is the target concentration. After distributing, this becomes a standard linear equation in x and y. The distance, rate, time template applies to 2 moving objects. Constraint 1 relates the distances based on the geometry of the motion. Same direction subtracts, opposite direction adds. Constraint 2 might fix the total distance, or the times relate through a known total time. Each scenario produces a system in 2 unknowns that the standard methods solve. Today's 2 examples cover the number, value, and mixture templates explicitly. Here is the first worked example. A jar contains nickels and dimes. There are 18 coins total worth $1.20. How many of each coin are there? The number value template applies cleanly one constraint on the count of coins, another on the total value. Step 1. Define the variables. Let n equal the number of nickels in the jar. Let d equal the number of dimes in the jar. Both are non-negative integers with units of count. Step 2. Translate the constraints into equations. Constraint 1 is total count n plus d equals 18. Constraint 2 is total value in cents. To keep the arithmetic clean, 5n plus 10d equals 120 because each nickel is worth 5 cents, each dime 10 cents, and the total is 120 cents, which equals $1.20. Step 3. Solve the system. Use substitution because the first equation has both variables with coefficient 1. Solve for any n equals 18 minus d. Substitute into the second equation 5 times the quantity 18 minus d plus 10d equals 120. Distributing 90 minus 5d plus 10d equals 120. Combine 90 plus 5d equals 120. Subtract 95d equals 30. Divide by 5d equals 6. Step 4. Back substitute d equals 6 into n equals 18 minus d. N equals 18 minus 6 equals 12. So 12 nickels and 6 dimes. Step 5. Verify in the original English. 12 nickels plus 6 dimes equals 18 coins total. Match. 12 nickels at 5 cents each give 60 cents. 6 dimes at 10 cents each give 60 cents. Total 120 cents, which equals $1.20. Match. Both constraints satisfied. So the jar has 12 nickels and 6 dimes. The big lesson from this example is the number value template applied cleanly. Define one variable per item type, write one count equation and one value equation, solve the system, verify in the English context. The same template handles tickets at different prices, products at different costs, problem variants where any two denomination items mix together. Recognize the template and the equations write themselves. Here is the second worked example. A chemist needs to mix a 30% acid solution with a 60% acid solution to produce 30 liters of 40% acid solution. How many liters of each source solution should she use? The mixture template applies one constraint on total volume, another on total acid content. Step 1. Define variables. Let x equal liters of the 30% solution. Let y equal liters of the 60% solution. Both are non-negative real numbers with units of liters. Step 2. Translate the constraints. Constraint 1 is total volume x plus y equals 30. Constraint 2 is conservation of acid is 0.3x plus 0.6y equals 0.4 times 30, which equals 12. So the second equation is 0.3x plus 0.6y equals 12. Step 3. Clear the decimals on the second equation by multiplying both sides by 10. 3x plus 6y equals 120. Now we have x plus y equals 30 and 3x plus 6y equals 120. Step 4. Solve the system. Use elimination by multiplying the first equation by 3. 3x plus 3y equals 90. Subtract from the second new equation 3x plus 6y minus the quantity 3x plus 3y equals 120 minus 90, giving 3y equals 30, so y equals 10. Step 5. Back substitute y equals 10 into x plus y equals 30, x equals 20. So 20 liters of the 30% solution and 10 liters of the 60% solution. Step 6. Verify in the English context. Total volume 20 plus 10 equals 30 liters. Match. Acid content is 0.3 times 20 plus 0.6 times 10 equals 6 plus 6 equals 12 liters of acid. 12 liters out of 30 liters total equals 40%. Match. Both constraints satisfied. So the chemist needs 20 liters of the 30% solution and 10 liters of the 60% solution. The big lesson from this example is the mixture template structure. Define one variable per source solution, write one volume equation and one solute equation. Clear decimals if needed for cleaner arithmetic. solve and verify in the English context. The same template handles concentration problems in chemistry, alloy mixing in metallurgy, blending in food science and beverage production. Mixture problems are extremely common in chemistry and applied science, and the template handles them all. 3 mistakes that catch every algebra student during their first weeks of system word problem work. Each one is fixable with a small explicit habit applied on every problem. First mistake: setting up only one equation when the problem has 2 unknowns. A student reads a problem about coins and writes only the count equation, forgetting that the value constraint provides the second equation needed to pin down the system. With 2 unknowns and only one constraint, the system is underdetermined and has infinitely many solutions, none of which is the intended unique answer. The fix is to read the problem carefully for all the constraints, then write one equation per constraint. 2 unknowns require exactly 2 constraints, 3 unknowns require 3, and so on. Second mistake: using the same variable name for 2 different unknown quantities, or defining a variable to represent a quantity that the problem already names with a different convention. A student in a coin problem uses X for both nickels and dimes, getting confused about which is which. The fix is to define one distinct variable per unknown at the top of the work with explicit units and to use those variable names consistently throughout the problem. The variable definition step is non-negotiable on every word problem. Third mistake: mixing units across the equations of the system. A student writes the count equation in items, but the value equation in dollars, while one of the per item values is given in cents. The unit mismatch produces silently wrong answers because the algebra works mechanically without checking units. The fix is to pick a single unit system at the start and convert all given quantities to that system before writing equations. For coin problems, cents is usually cleanest because it avoids decimals. For mixture problems, decimals or fractions are unavoidable, but should be consistent across both equations. System word problems are extremely common across standardized tests, finance, manufacturing, and applied science. Anywhere 2 or more unknown quantities interact through 2 or more constraints, a system of equations captures the structure cleanly. 4 broad sectors below. On the S8, ACT, GRE, GMAT, and most state algebra exams, system word problems appear on every math section. Number, value, mixture, distance, rate, time, and age problems are the most common templates, and recognizing them on site unlocks fast solving. Test prep books often include dozens of practice problems organized by template because the template recognition skill is what separates fast solvers from slow ones on these exams. The skills you build today are directly testable on every standardized math exam. In finance, investment portfolios split between 2 assets with different expected returns produce a 2-equation system in the unknown allocation amounts. Constraint 1 fixes the total investment amount, constraint 2 fixes the target portfolio return. Solving the system gives the optimal allocation. Similar systems appear in loan portfolio analysis, insurance underwriting, and many other dual constraint financial decisions. The number value template generalizes directly into these financial scenarios. In manufacturing and operations, production schedules that allocate time or material between 2 products with different requirements produce 2-equation systems. Constraint 1 might fix total available time. Constraint 2 fixes total available raw material. Solving gives the production split that uses both resources fully. Linear programming generalizes this kind of analysis to many products and many constraints, but the algebra level intuition starts with the 2 variable systems we cover today. In chemistry, biology, and pharmacy, mixture problems are pervasive. Concentration adjustments in lab reagents, dose calculations for compounded medications, blood type ratio analysis in transfusion medicine, and many other applied scenarios use the mixture template. The chemistry connection is especially direct anytime two solutions of different concentrations combine to produce a target concentration. The mixture template applies and the resulting two-equation system gives the volumes needed. 3 things to take with you from this lesson today. System word problems are the main practical use of the system solving algebra you have built across this section, and they are the form of problem you will encounter most often on standardized tests, in homework problem sets, and in applied work across many quantitative fields you may study later. First, a word problem requires a system of equations when there are two or more unknown quantities related by two or more constraint statements in the problem. Each unknown gets a variable, each constraint becomes one equation. Two unknowns require exactly two equations, three unknowns require three, and so on. Setting up only one equation when there are two unknown quantities produces an underdetermined system with infinitely many solutions, none of which is the intended unique answer to the question. Second, several common templates account for the majority of system word problems you will see. The number value template counts items and sums their values. The mixture template combines two solutions of different concentrations to produce a target concentration. The distance rate time template relates two moving objects through their distances, rates, and times. The age template compares ages of two or more people at different times. Recognize the template instantly on every problem, and the equation structures follow without derivation. Third, the four-step framework from Section 3 adapts cleanly to systems. Define one variable per unknown quantity with explicit units written next to each variable. Translate each constraint statement in the problem into one algebraic equation, producing as many equations as the problem has constraints. Solve the resulting system using substitution, elimination, or the graphical method as appropriate based on the coefficient structure. Verify the solved values in the original English context rather than just in the algebra. The verification step is even more important for system word problems than for single equation problems because there are more places for translation errors to slip in along the way. Reading the original problem one more time after computing the answer and confirming all constraints hold at the solved values is the cheapest insurance against silent translation errors, and it should be a non-negotiable final step on every problem. The system word problem skill scales naturally to 3 variable problems with 3 unknowns and 3 constraints, and to higher dimensional systems in linear programming and operations research courses you may take later. Today's 2 variable templates are the foundation, and the strategies extend uniformly to larger problem sizes through repeated application of the same workflow. Coming up next, the lesson called Systems of Inequalities, where we extend the system solving toolkit from equations to inequalities. The solution to a system of inequalities is a region of the coordinate plane rather than a single point, and the resulting feasible regions are the foundational tool of linear programming and constraint optimization across operations research, economics, engineering design, and many applied fields you will encounter later.